Let's talk about refinement. And I'm Pavel, doing refinement in Phenix for the past 20 years. Um, we have 60 or even 59 now minutes to talk about refinement. Refinement is a big topic. To cover it in great detail, so I'll probably need 3 days of 8-hour slots every day to get everything covered. So don't expect me to talk about everything today. What I have is just accumulation of random topics that I believe relevant, and I count on you to ask questions. Right. So again, like I said, no way I can cover this in great details. I'm just giving hints in my talk, and I rely on you to ask questions you have. Don't be shy, ask questions right away before you forget them by the end of my talk. And again, I realize we don't have enough time to cover everything. So if you have big questions, we can talk more after the talk, or we can discuss that by email, or my email, so we can always set up a Zoom and talk about this, or whatever you have after this presentation. Cool. All right, let's get started. So refinement is, what is refinement, right? So I'm going to jump between very basic and sometimes advanced items in the list. So we're all on the same page. I realize we are a mixture here of experts and novices. So refinement is one of these stages in the procedure of solving a structure. It's crystallography, going from samples, crystals, data processing, solving your structure by one or another method. And then refinement is one of the steps, but it's a very important step. If you eliminate the step, you won't be able to publish your structure at all. So you won't have all these 200,000 structures in the protein data bank, because refinement is the step that makes all the structure to conform prior knowledge, prior expectations, to pass the validation. So without refinement, you wouldn't be able to publish your structure. So refinement is a totally crucial step. And also refinement is the least automated step. This auto building trays, so all those methods, they're very automated. They're very automated. You push the button, you give it a sequence and data, you push the button, and you wait 1, 2, 3, 24 hours, 2 weeks, and you get your structure. From refinement, we all expect a refined structure within minutes, or worst case scenario, hours to come out. And for this to be practical, we have to take shortcuts. And so refinement is the least optimized procedure we have, just because to make it interactive. You change something, you are refinement, you get the result. If refinement would take a week or two, that wouldn't be very practical. So refinement is least automated, and therefore is most reliant on your expertise to set it up correctly. So you get most out of refinement, right? Again, refinement, just in a little bit more detail for those who are less familiar with refinement. Refinement is an optimization procedure which requires three entities. It requires inputs, data, and model. And model we fit to the data, some prior knowledge to compensate or to bring extra information into the procedure. We need a score that defines how well the model fits to the data. We need an optimizer that knows how to change the model to optimize to the data. That's a cyclic procedure, and as a result, you get an improved model, hopefully. So that's in a nutshell what refinement is, and this is just a graphical illustration of that. So map, data, and refinement moves, map model and refinement moves model to the data. So that's what refinement is in a nutshell. Okay, so this is something I keep showing all the time, because there are multiple tasks in crystallography, but in cryo specifically, and they're all similar to refinements, but not all of them are refinements. So docking specifically, flexible fitting, morphing. So all these methods, they kind of move your model to the data. What's the difference? The difference is by how much they're supposed to move your model to the data. When you have a docking problem, you have map here and model miles away from your map, and docking is supposed to somehow bring map and model together. So this situation is totally outside of the scope of refinement. So if by mistake you apply refinement to this situation, refinement will fail. And it's not refinement's fault. It's your fault to not use the correct tool for your job. Same applies to flexible fitting. So we refer to this as radius of convergence. So these different tools have different convergence radius, and docking has pretty much unlimited convergence radius, while refinement has convergence radius of 1, 2, or maybe 3 angstroms. So your model needs to be at worst 3 angstroms away from the correct answer for refinement to work. Right. So that's something to realize. So don't try to run refinement when you have a docking situation, for example. And the reason why I show this slide is because I keep getting user complaints who try to having docking situation, they try to run refinement and say, oh, refinement doesn't work, I get 0 correlation, your program sucks. And no, that's just because you use the wrong tool for the job. So these days, refinement is, even though I told you this is least automated, but still, when you run refinement in Phenix or CCP4 and other software packages, it's presented to you as a pretty much black box. So you drop in data and model files, maybe some restraints, zip files that Nigel was talking about this morning, and then you push the hit button, push the run button, and take some time, usually within minutes, seconds, hours maybe, and you get a find model. So that's how we see it from the GUI view, graphical user interface view. So the good question to ask is, does this always work? Right? Does this always work? Is it always like you get a bad model as a start and you expect a better model as the end of refinement? So these are really good questions to ask yourself when you do this. And sadly, the answer is no. It's not always the case. So it is a lot of the time, it is the case, but it's not always the case. Why is this? Is because refinement parameterization is not easy. There are a lot of different scenarios dictated by the data quality. Thinking of crystallography, what is data quality? Presence of twinning, mosaicity, resolution, data completeness, all kinds of solving content, space groups, symmetry. All these things go into play and tend to complicate your refinement. And default settings of refinement are tuned to work in the most typical scenario. And what is most typical scenario? It's 2 angstrom resolution data set, no twinning, no pathologies. Everything is nice, solving content 50%. So it's easy. That's the majority of structures solved and deposited in the PDB with all these metrics. So that's the default settings that when you run refinement in Phenix and just give the model and data and hit run button, that's the parameters used to conduct refinement. But if you have anything unusual, you have very low resolution data, 4.5 angstrom resolution data, yeah, or incomplete data set, or highly anisotropic data set, or you have twinning, or you are blessed to have ultra high resolution data, like 0.7 angstrom resolution X-ray data, then you have a lot of details, lots of alternative conformations, deformation density, and so on and so on in your maps. So that requires extra attention and your knowledge to parameterize refinement so it works correctly in this particular case. And this is not what is going to be handled in the default mode. So software will rely on your knowledge to parameterize refinement correctly for all these corner cases, which are really, really numerous. Okay. And of course, when you up to do that, you will be up against a lot of jargon and a lot of things that you need to know about refinement. You'll need to know about what is NCS, what is simulated annealing, what is CDL, what is clashes, Ramachandran, and so on and so on, because that is what required from you to parameterize refinement correctly. Now, this is not to discourage you, not to say this is too complicated so you cannot do it. It's just to make you aware that if you are away from the average situation, then refinement software expects you to provide meaningful input, so it gives you a meaningful output. Right. So now, what to do when the black box does not work? And this is just exactly what I just said. Your decision making is important, because otherwise it will follow the default pathway, and that's not going to be the optimal one. And well, the next question, which is reasonable to ask, is, okay, well, I did what I could, but how do I know refinement worked? How do I know I did what I did is, it's correct? And how do I know when to stop? I keep changing my structure, keep polishing it, but when do I stop? And the universal answer, which I'm not going to talk about, Christopher will talk more about in greater details. We don't have time. Usually I talk about it, but we don't have time today. Is to do validation. So validation by now is quite a mature standard procedure with very powerful tools. And those tools are supposed to answer your questions about when I stop, am I good to just publish my structure, or do I need to do more work? Do validation, and Christopher Williams will talk more about it. Now, as I promised, I just picked random topics that I believe relevant and that I believe can fit into the time slot that I have. So, and refinement has many hearts, many important pieces in the procedure, but I believe the score is one of most important. So I decided to talk about it more today. So what is refinement score? Refinement score is a function that dictates the quality of your model in terms of how well it fits the data, experimental data, at the also requirement to obey prior knowledge. And prior knowledge, what is prior knowledge? Prior knowledge is your structure needs to be chemically meaningful, it needs to be physically meaningful, it needs to be crystallographically meaningful, it needs to be meaningful in all the senses, right? And how we formulate all of this, what I just said, well, it's a mathematical formula, which I'm showing here, and typically and universally across most software, it just has two terms. So the first term defines how well your current atomic model fits the experimental data. And in crystallography, experimental data are the fraction intensities, so amplitudes, and cryo-EM, experimental data is the map, three-dimensional reconstruction. And the second term brings extra information to refinement to make refinement actually possible. And that extra information is meant to compensate for imperfections of experimental data, which is always the case. Your experimental data is never perfect. It has finite resolution. You never collect your data up to infinite resolution. So it's always 1, 2, 3, 4, 5 angstrom resolution data. It has experimental errors. It's not complete and whatnot. So if you just refine your model against the data, the model parameters will absorb all the errors in the experimental data that are present in experimental data. And your model will have all these errors. This is something you really don't want to have. This is why we dose this extra information into refinement, and we dose this extra information with a weight. So this refinement weight, you will hear about this weight if you ever do refinement. You'll hear it a lot because this weight is totally critical because it doses extra information into refinement. When you have high resolution data, this dose of extra information needs to be relatively low, but as you progress towards lower resolution data, meaning there's less information in the data, but you need to compensate the lack of information in the data with extra information, this dose of extra information needs to be higher. And that's dictated by this refinement weight, which is a very important parameter. And just to illustrate what I said, what if you have your experimental data and model already and you refine it without this extra information? Typically, that's what's going to happen. If you use restraints, well, that's what we do all the time. But if you don't include this extra information, atoms will rush into the map, into the data, but the model you get as a result is not going to be quite chemically meaningful. As you can see, there's this tyrosine ring is distorted, not planar anymore, for example. Even though the map looks like quite nice tyrosine side chain, and with a hole in it and inside, but all these errors associated with the data will make this data not perfect, and therefore, if you don't use extra information, this is what happens. So model will just move to the data, feed it as good as it can, but it's not going to be chemically meaningful. That's what's called overfitting. So you'll get a better score, model to data score, at the expense of poorer chemistry and geometry. All right. Now, we've been talking about standard restraints on covalent bonds and angles and planes, standard typical resolutions. But if you happen to work with low resolution data sets, that typically happens when you do cryo-EM, sometimes crystallography, and by that I mean resolutions worse than 3.5, 4, 5 angstrom resolutions, then even standard restraints are not sufficient to maintain your model geometry correct chemically and physically. And actually illustrate this with the following example, where I have a perfect helix. So this is a stretch of perfect alpha helix, which I place in a sausage of 5 angstrom resolution map. So everything is perfect, except the map is 5 angstrom resolution. And if we refine this perfect to begin with, alpha helix against this map with standard restraints, and standard restraints include bonds, angles, planes, torsions, but we don't tell the refinement procedure this is an alpha helix, right? So what's going to happen is atoms are going to move around to fit the map, this powerful slow resolution map, as good as possible. But as a result, you get an accumulation of atoms that fits the map better than we start out with. But this is not an alpha helix anymore. So that highlights importance of bringing extra information into low resolution refinement in addition to standard restraints, and that highlights also troubles related to refinement against low resolution data. And basically, that's a summary of what I just said. In addition to standard covalent geometry restraints, we need to bring all the other information we know about your protein or DNA, RNA molecules, such as secondary structure, Ramachandran plots, side chain conformers. All that information is helpful and mostly needed in refinements if you refine against low resolution data. So that's very important if that's your case. Now, just moving on, because as I said, I'm just bringing various topics. So in Phenix, we have two tools for refinement, specifically designed for crystallography, specifically designed for cryo-EM. And those are referred to by the command line names. Phenix.refine is for crystallography, Phenix.realSpace_refine for real space refinement in the case of cryo-EM. They're conceptually very similar. Under the hood, they are very, very similar. And the differences arise at the level of inputs. In crystallography, you start out with a model and diffraction intensities. In cryo-EM, you start out with a map. But the rest is very, very similar. And this is how it looks. The entire procedure, again, this is very generic. Same happens for crystallography and cryo-EM. So you start with data and model, and there is a cycle which we refer to as macro cycle of events, which includes coordinate refinement, B-factor refinement, occupancy refinement, calculating weights, fitting rotamers, doing individual coordinates refinement versus B-factor refinement. All these different steps that potentially can happen during refinement, either by default or if you request that to happen. And that repeats several times, 3 or 5 times by default, and you get your refined structure and log file with a lot of information about refinement statistics. So that's in a nutshell what happens in refinement. Now, from this point on, I'm going to go across very specific topics, and this is mostly inspired by questions that users ask at mailing list, Phenix bulletin board, or CCP4 bulletin board. So I have statistics of these questions, and I just take top N questions that can fit in the time I have. So that's how I do this typically. All right, so let's go one by one until I run out of time. So hydrogens, do I use hydrogens in refinement? This is a very popular topic. And the answer is yes, you do need to use hydrogens in refinement, and I'll try to convince why. Well, first off, hydrogens do contain about half of your protein structure. So what I show here is a snapshot of a random structure without hydrogens and with hydrogens. As you can see, here hydrogens make a lot of contacts between atoms. What that means is if you refine your structure without hydrogens, so look at this atom and this atom here, right? So there's 2 atoms. There are no hydrogens, and you know the data is not perfect, finite resolution, lots of errors and whatnot. So these atoms during refinement may by accident just get too close to each other, generating a clash. And when you do validation, the animal probability will complain and say, oh, there's a clash there. It's a problem. You need to solve it, right? While if you do have hydrogens, then suddenly these atoms are aware about hydrogens and they wouldn't come close enough to generate a clash because you have explicit hydrogens. So at least for this reason, it's good to have hydrogens because you will get chemically more meaningful structures out of your refinement. Other things keep in mind is that hydrogens still do contribute to R factors. Not a lot, but up to 1% gain you can expect if you include hydrogens into refinement. And believe it or not, hydrogens do contribute to lowest resolution range of structure factors, not the highest one. So hydrogens is a good thing to include into refinement with a nuance that you don't want to include them in the very beginning. You do want to include them towards the end. Why is that? Is because it's a lot of atoms. If you add hydrogens, there will be a lot of atoms in your structure. And if you are in the beginning, when you build your structure semi-manually, automatically, just having more atoms is more complicated to deal with your structure. So think of getting your structure almost there. And once you're almost there, add hydrogens and continue having hydrogens from that point on and deposit your structure with hydrogens. So that's the bottom line of this. And this is just another example to convince you hydrogens are important and helpful. Sometimes they allow you to disambiguate ambiguous situations like shown here. Some residue side chains have nitrogen and oxygen in the side chain, right? And they're pseudo-symmetric. So how you choose which one is correct in this example, right? So that's tricky. If you don't have hydrogens, you can't really do this. But if you add hydrogens, suddenly you realize in one example, you have clashes, and another one, you have favorite non-covalent interactions. So adding hydrogens can resolve situations like this. And by the way, this happens automatically in refinement, but still that does not diminish the value of having hydrogens. Also, I'll use this opportunity to make you aware about neutron diffraction. So if whatever you do in your research is related to hydrogen, and hydrogen is important for biological question that you work on, so consider neutron crystallography. Neutron crystallography is very much like X-ray crystallography, except that in neutron crystallography, you get experimental information about hydrogen atoms, and neutron crystallography resolves hydrogen atoms as well as good as all other atoms. So if you do neutron crystallographic experiment, you may get information about hydrogens of your biological question. In this picture, I'm just showing as an example, as that's the reduction structure. So this is X-ray map, 2 false minus of calc map, very high resolution, unusually high resolution for X-rays, where hydrogens are not quite known. So right, it's pretty obvious here. And similar neutron map, 1.7 action resolution, where hydrogens are very well resolved in this map. So again, if hydrogen is important for your research, consider neutron crystallography. It has limitations related to crystal size and data collection times and the requirement to do deuteration of your sample. But these are issues that are progressively becomes less and less important. There's a lot of technological progress in that direction, and there are national facilities to do neutron crystallography in the States. It's in Oakridge mainly, and lots of Euro facilities in France and Sweden. So there are ways to get your neutron diffraction data if that's something interests you. Another topic I wanted to mention, I mentioned that in the beginning, so when to stop. And there are tools to tell you something about this in different software packages, and PDB also has that. In Phenix, we have a tool called Polygon, which basically, what it does, it compares your structure that you're refining at this very moment with respect to all other structures in the protein data bank at similar resolution, plus minus. And here we have each bar here represents a histogram of particular values, metrics, such as R-free, R-work, bond angular MSDs, average B factor, for example, can be different. It's customizable. The dot connecting those lines here is where you are with respect to this histogram at this very point, right? So if you happen to be in the middle of each histogram, that means you're very similar to thousands and thousands of structures available in the PDB. It's a good sign. You're very similar. It does not mean you don't have local errors in your structure. That's a good sign saying you don't have anything outrageously different compared to everybody else. And this is just basically what I just said. So if you have a polygon picture looking like this, that means you're very similar to everybody else. It's a good start. It's good to have that. Again, that does not mean you don't have local problems. But if you have something like this, that means you really need to worry about and do something about it, because you're so dissimilar. And either you need to explain why is this, or you need to work more on your structure to address this. That's the bottom line. And this tool is these plots are actually presented to you every time you run refinements. Every time you run refinement in Phenix, you get these plots. I know not many people click on that little icon to look at these plots, but I highly encourage you to do so because that actually gives you extra information. Another topic that I like to mention is local versus global. A lot of people I know solve this structure and grind and refine and do things and just watch our work, our free number of Ramachandran plot outliers, clash score, bone angle RMSDs, and these are a handful of metrics that people use to decide where they are in the process. But these are global metrics. These are used to calculate all the atoms in your structure. But what if you have a ligand in your structure that's got distorted for whatever reason? You probably supplied the wrong CIF file that Nigel was talking about a lot this morning. Or for any reason, if something happened to your lovely ligand and you never looked at it, you will never see that if you look at our work, our free bone angular MSDs. So because this is just a tiny fraction of all the atoms in your structure. Take-home message for this is please look at all the validation statistics that Phenix refinement presents to you. So every time Phenix refine, finish, get a lot of information in the form of just numbers and tables. And those tables present you this information per atom, per residue, per chain, and so on and so on. So detecting this is a matter of looking at these tables, right? All else, it's very easy to overlook this information. Or this problem, actually, not just information. Then another thing I like to mention is, and again, because this is very, very, very common topic that I keep seeing on mailing lists, is if you refine your structure and it contains heavy atoms, anything heavier than typical protein atoms, which is nitrogen, oxygen, carbon, sulfur, hydrogen. Say you have a heavy atom derivative in your structure to solve your phase problem, like in this example, I think it's cadmium. Well, just because this derivative is so much more electron rich compared to all other atoms, this only fact means it amplifies all the signal as well as all the error up compared to all the other atoms. And when you see something like this, that may mean several things. One is there's an error there, and it's amplified to scream at you and say, do something about it. Or it may just mean that everything is fine, except that all these artifacts are due to the fact that all the errors that all other atoms have been amplified because this atom has more electrons. So if you, in this situation, if you scroll down your electron density map sufficiently low enough, you probably see the same picture for all other atoms, carbons and nitrogens and oxygens and so on. So what do you do about this? Answer ranges from nothing to refine anisotropic B factors, because sometimes these atoms, the data contains enough information to support an anisotropic B factor refinement. Include charges, because it may happen that you included this particular ion where it's neutral charge, but it's actually charged, and therefore use wrong scattering factor, and that's the way for this ion to tell it to you. Multiple scenarios in this. There is no one-stop answer to this, but just be prepared to deal with this. That happens, and sometimes you can do nothing about it, and sometimes you can take steps and resolve the situation. Also, again, this is next topic. Like I said, I'll be jumping between topics. Don't expect refinement to solve unsolvable, right? So, and again, this is inspired by So if you have a situation like this where you have, and this is borrowed from our colleagues at no probability side. If you have something like this, refinement probably is unlikely to solve it because that requires model building and sometimes manual model building. So don't expect refinement to solve things like this. Sometimes it can, sometimes it cannot, but just keep that in mind. So it's still important to look at your map before you deposit and publish it, right? And by the way, this example is still in the PDB, I think. At least 1 year ago, I checked it and it's still there. It's still there. I think, well, it's still there. And that's not the only one. That's a lot of like this. Low resolution refinement. So this is just suggestions for you if you unlucky enough to work at low resolution with low resolution data. General considerations, you better use all the information available to you to make refinement stable and produce chemically meaningful structures. Use Ramachandran plot restraints, secondary structure restraints, reference model restraints. What is reference model restraints? I didn't have time to talk about it, but it's basically if you refine your structure against low resolution data, and you happen to know that there is a similar structure in the protein data bank of a high resolution homologous structure. It doesn't have to be 100% identical. It could be 60% identical or something like that. That structure can be used as a source of restraints, source of extra information for your low resolution refinement to help your low resolution refinement. So there's a machinery to do that in Phenix. We can talk about it more if anyone interested after the talk or later. But just keep in mind, so if you refine your low resolution structure, and you can always use high resolution structure that might be available in the PDB if it is available. If it's not available, you're out of luck. All right, so that's broadly suggestions for low resolution refinement. Now, we did not have time to talk about it much, but when you do refinement, you probably will hear things like simulated annealing or morphing in the context of refinement. So these are basically aggressive techniques to optimize your model against data. So most of the time, when you run refinement, under the hood, we use gradient-based optimization to optimize your coordinates, b factors, not against the data. There are more powerful techniques to move your model in order to bring you closer to the data. It is called simulate and model morphing. Those tools, broadly speaking, have larger convergence radius. What that means is in standard refinement, you just start, this is your data, this is your model, and this is only so much the model can move. While what happens if your model is here, like 5 angstroms away? Then, well, in this situation, things like simulated and morphing can help because they can move models more in order to fit your data. So these are very great tools, helpful to, in the initial stages of your refinement, you solve phase problem by molecular replacement. Good idea to run simulated annealing-based refinement or do morphing. But you never do this towards the end because these are aggressive. Aggressive means they can do better or worse. So you don't do it towards the end. That's the bottom line here. Now, I made a very controversial statement about using Ramachandran plot restraints always at low resolution. And I'm very surprised that nobody screams and saying, hi, that's Ramachandran plot is our validation tool. And if you use that tool as part of refinement as an active validation, as an active refinement target, that tool will lose its validation power. So if you use Ramachandran plot as a refinement target, then it's it loses its potential as a validator. Well, there was a choice here. You either produce chemically more meaningful model and sacrifice validation by Ramachandran plot, or you produce radish model, but you can validate and tell it's radish by using Ramachandran plot. So that's the choice here. The bottom line is I still insist in saying that it's a good idea to use Ramachandran plot as restraints for low resolution refinements, with a nuance, with a caveat that you are not supposed to use this tool to fix outliers in your model. And I'm going to pictorially illustrate my point about it. So by using this example, 5A9Z, so this is the original structure that is if you download it from PDB and calculate Ramachandran plot for this structure, that's how it looks like. That's the plot. Looks pretty terrifying. Yeah, I hope everybody agrees, right? And if you are, the person who is up to fix the structure, a very naive but wrong approach would be to take that structure and run it through Phenix real space refine with Ramachandran plot restraints. So one command or one click in the GUI, just dump model and data, click. In 10 minutes, you'll get a structure that has this Ramachandran plot. And that's a problematic Ramachandran plot. And I hope you see, but if you don't see, we will expand on this. So yes, Refinement will do a very good job at getting rid of outliers and creating a structure with this plot, but this plot is quite problematic. It's problematic because what we expect is something like this, right? So we know how they distributed, but this guy look very, very artificial. Now, you do need to use Ramachandran plot restraints to prevent outliers from happening, but not to fix them. So basically, in that previous example, what you need to do is you need to get your structure to this stage where there's no outliers and you made sure it makes sense, and then use Ramachandran plot restraints to keep them there. Because if you don't, then if you start out with this kind of structure and Ramachandran plot and refine it against low resolution data doesn't have information, doesn't have enough information to keep your structure in place. So residues will drift away and become outliers, and it will get back your nonsensical distribution. So Ramachandran plot is good at keeping good model good, but it's bad at fixing things. Right, and going back to this question, so this is what is wrong is, as you said, it's not natural. It's very, very systematic. And we know what the good distribution looks like, right? Why? By looking at many, many, many good structures available to us. We know what is the good plot and how it's supposed to look like. How we formulate that as a numerical metric. So how we link our visual perception to something that we can formulate numerically, right? So let's consider this plot, right? So we have a good plot, right? So nobody would argue this is a good plot. This is good too, even though it has two outliers here, but these outliers can be justified in this particular example. It can be justified by electron density map because there is some chemical interaction creating strain, and it can be justified. Now we know this is bad for sure, right? But all other plots that you can find in the database, like this or this in the middle, this on the right, they're technically perfect. From the table 1 viewpoint, they are totally perfect. They have proper number of residues in favorite, most favorite, outlier regions. So from table 1, they are absolutely perfect. But if you look at actual plot, you realize that's terrible. I don't know what is wrong, but that's something wrong about these plots. So, and there is a lot of situations in between. So I'm showing you extreme examples, but a lot of situations in between, less obvious than this. Now, how we deal with this, right? So if you refine your structure and you solve your structure, or you are working at protein data bank and you have to validate hundreds of structures, you don't have time to look at all of this every time. So can we handle this in somewhat automatically, right? Well, it turns out that this very question, this very problem was addressed a long time ago, back in 1997, by these researchers who proposed to calculate one number, which is called Ramachandran Z-plot, based on your structure. So you calculate in a fraction of a second one number, and that number has a very clear, very obvious interpretation. So it basically, based on this number, you can tell my structure is rubbish, it's strange, or it's good. So very trivial interpretation in a matter of a second, less than a second. And this is something we rediscovered, and Oleg, who is going to talk next, implemented in Phenix, together with our collaborators and colleagues in PDB-redo. So it's available now, and we make a heavy use of this metric, and we show it everywhere, and we encourage you to use it as well, because this is a number that allows you to tell a lot about your structure without actually looking at plots and making your subjective decisions. And now if I bring back all these plots along with these numbers, it makes it pretty obvious. So the good plot has a very good Ramachandran Z value. The good plot with outliers also scores well. The bad one is bad, and that number tells you it's bad. And all these suspicious ones that, naively you would call good because they don't have any outliers, everything can be favored and not regions, they score as impossible. They're very bad by this metric. So that, keep in mind, Ramachandran Z is super powerful, super good metric that we universally use in Phenix these days. And not only us, but our colleagues at PDB-redo. Switching gears again, don't be too religious about outliers. Sometimes outliers can be real if you can justify them against your experimental data. So if basically what that means, if you have an outlier, geometric outlier, Rotem outlier, Ramachandran plot outlier, or some other kind of outlier, if you can justify it by your experimental data, if you can tell, oh, this outlier happens because there is some interaction chemistry going on and it's in the density map, you're fine to have it. But if you cannot do that, you better get rid of that outlier one way or another, because it's not supported by your experimental data. And the next guy, a reviewer like me, would question that. So just keep in mind, an outlier does not equate to wrong. But if you have one, you need to justify it. That's important message here. Okay. So what other things I wanted to mention you? Oh, this is another topic that again inspired by questions I get on mailing lists. So Phenix Refine, around Phenix Refine, you get a lot of outputs. Most of the time, of course, you care about your PDB file with the model that you load and code and maps, right? But just so you're aware of this, there's a log file that Phenix Refine creates, and log file has a lot of information, a lot of technical information. Most of the time, you don't care about. But if there's a problem, that's the time when you need to look in that file. And if you contact us developers about particular situations and problems, just be aware there's a log file to look at. Again, sometimes people even don't know there's a log file, so I mentioned that. There's also file with extension .eff. That's the parameter file that lists all the parameters that Refinement used. And sometimes we ask you to use one another parameter, and we ask you to, if there's a problem, we ask you to send us the parameter file. So that parameter file lists all the parameters used in Refinement. And also it's a way to double check if some specific parameters used in Refinement actually were used in Refinement. So that file actually lists this file, the parameters. MTZ file, we'll talk next. And geofile, Nigel mentioned that, but I will second it again. So geofile lists all the restraints used in Refinement. So if you care about particular bond between your ligand and protein or something else, some non-standard interaction, you expect that bond or angle and whatnot happen to be part of restraints. The way to check if that was actually in Refinement, check geofile. Geofile lists all the restraints. Gigantic text file that lists everything. So you just use your favorite text editor to find that particular restraint. Now, enter that file. And this is something I like to mention because, again, I get a lot of questions. What's in that MTZ file? A lot of information there. So MTZ file out of Phenix Refine. Phenix Refine always produces file with extension .mtz. That file contains 4 blocks of information, 4 blocks of information presented as arrays of numbers of values. So the first one contains the copy of input arrays that were used in Refinement. So if you give it f-ops and R3 flags and Hendrickson-Lachman coefficients, that will be just copied into that MTZ file, right? So that's the first part. So the second one is arrays are actually used in Refinement. What's the difference between these two is because sometimes you say, oh, I want to truncate my data by resolution, or you come in with intensities, but Refinement always uses amplitudes, so it converts intensities into amplitudes. So what actually used in Refinement may or may not be exactly the same as your input files, as your input data. So that's why we have the second entity in under that file, that the data actually used in Refinement. It may or may not be different from the first one, right? The third one is the total structure factor calculated from final atomic model. So the structure factor includes your final atomic model coordinates as well as all the parameter that describes your crystal. The bulk solving, twinning, and isotropic scaling, all other scales. So the structure factor is best to use to replicate R factors that you report. So if you ever happen to have that quest of replicating structure R factors that you published, and somebody questions, they doubt in your R factors, you can use this F model to replicate your R factors. And the last block contains your maps in terms of Fourier map coefficients. And those are 2 f-ops minus f-calc maps and difference maps, f-ops minus f-calc maps. What will you see by default in Qt when you open these maps is what we call field maps, the maps where missing reflections in your data set are filled with some statistically expected values. And that's very important nuance. So, and let me explain that in a little bit. So basically, if your data set, yeah, sure. Oh, you can continue explaining this. Right. The thing is, if your data set is incomplete, that affects quality of maps a lot. And what we do against this is we we fill in missing slots in unmeasured reflections with some expected values. And what that means is we infer these values from actual structure that may bias your map with respect to structure that you have at hand. So bottom line is, if you have very incomplete data set, when you load your MTZ file in Qt from Phenix Refinement, your 2 Fox minus of calc map may be model biased because all these unmeasured reflections were filled using your current model. And you may want to manually switch to not filled reflections, not filled 2 Fox minus of calc map that's available in that MTZ file, but you need to do it manually. Right, so this is a little nuance, probably never happens to most people, but if you have incomplete data set or you subjected your data set to an isotropy truncation server, so things like this, something to keep in mind, right? PDB deposition is very related to refinement because refinement is next to PDB deposition step, right? Just to make you aware, once you've done with refinement, the next step you do is you run all the statistics necessary for PDB deposition and publishing your paper. So in the GUI, there is a tab called PDB deposition. And this is where you get your table 1 for the journal. You dump all the data you have, and that gives you a nice frame table 1 that you can copy paste into your paper, structural paper. It's supposed to work well. You can also get your PDB validation report even before you actually submit your structure into the PDB. That's also helpful. So that's just aware of that because I believe these are slightly underused tools in Phenix. This I can safely skip because Nigel mentioned we are all mmCIF these days, right? So we are, like it or not, but we are moving towards mmCIF. Just a few notes about mmCIF. Contains a lot more information than PDB, but it's not human editable. You're not supposed to edit. Unlike PDB file, it's very easy. It's called columns. It's trivial to change something in these columns, add an atom, delete a water, trivial. In mmCIF, it's all integrated into internal data structure with all these loops and everything. So if you just change the characters there and then you invalidate the entire file. So it's not really meant to be human editable. So mmCIF files, my best advice, never touch it, never edit by hand. Right. Phenix generates mmCIF files. Most Phenix tools generate mmCIF files, so normally should not need to edit it. Right, and like I said, editing by hand is tricky and can lead to hard to recover errors. And that brings me to the final, most important slide. So if this is something you can learn from this, that's the most important one, because again, we have no time to cover everything. Right, so if you have any problems running software, or if you have any questions running software, just don't give up and get in touch with us. And these days, I tend to, if I realize we benefit from a discussion, so I tend to suggest having a Zoom meeting and discussing things. If you have a question, we just might be better have a Zoom call and talk, or if it's trivial, we can discuss it by email. But that's the general idea. So you have a problem, talk to us. And poor way to report a problem, just say, oh, I run that program X in Phenix and it crashed, so your program sucks, I don't know what to do. Well, that's a poor way. That's not helpful. That's not helpful to you, not helpful to us. Usually, better way to do that is to tell us a way to reproduce your problem, because the only way we can actually help, we need to replicate problem you have. So you run something and it crashes, and you report it to us. The only way I can help you, I need to do the same as you did on my computer, get the same crash or same misbehavior, whatever, and only then I can help. If I cannot reproduce it, I'll give up. I'll say I cannot reproduce, I cannot help. Sorry. So just keep that in mind. And sending us data is safe. We're not going to publish your data. We'll just help you and throw it away safely. And that concludes my talk today. Thank you very much.